welcome you to the 15th lecture in the series of marine hydrodynamics. And in the last lecture, we are talking about, I have introduced to you about aerofoil sections, and then we have talked about how to transform a symmetry from a circle to a symmetric aerofoil by using the Joukowsky transformation. So, towards the end of the lecture, I had mentioned that we can, if we shift, because we had done a vertical horizontal shift. So, from a circle, if we are applying the Joukowsky transformation, so we are able to transform a circle to a symmetric aerofoil. But what will happen if we transform the circle using the Joukowsky transformation, and the circle is shift, both there is a horizontal shift and there is a vertical shift, and then we will apply the Joukowsky transformation. Then it is obvious that there will be a shift towards in the upward direction, and that will give us the cambered aerofoil, which looks like a typical aerofoil section of an air wing. So, let us look at this, that how we are going to do this before proceeding further about the theory of aerofoils. So, with this, so let us first do the transformation. The transformation of a aerofoil, transformation of a circle into a cambered aerofoil profile. So, to do so, what we will see, that suppose we have a circle, as I told you. In the circle, what we are doing, suppose this is the line through the origin, and then let me say that O is the origin of the circle and this distance, and then what I am doing, I say that let the horizontal shift be n, and this is, and then there is a vertical shift, that is, and C is somewhere here. So, O is the origin of the circle and C the center of the circle. O is the origin and C the center of the circle. So, in that case, what I will do, I will say let the distance as usual, let O n is B E, and again O n is B E, while the shift is the distance C n, and let C n is equal to H. This is the vertical shift, and O n is B is the horizontal shift, and then we have M O, we have my M O is B, M is a point here, M O is B. Then what will happen? Now, what I will do, I will take any point, let me say, suppose P is any point on the circle, If P is any point on the circle, then what I will do, I join this OP, then and then P is, if I say this is a angle is theta and this distance is r. So, P has the coordinate r theta and C is the center of the circle, let me call it join P C. So, P C is the radius of the circle, and let me call this radius of the circle is A. Then we have, and then again, if what I will do, I will join the point M with C. So, my MC again, because this is a point, this is the center, MC is also A, and then I have two things here. My with this understanding, let me say that this angle, let me say this is beta, and then the angle it makes with this, let me call this as gamma. So, if I take this, then what will happen? Now, what I will just separately plot these points. So, let me call this okay. Let me do it separately, that will be very clear. So, basically I have this point is M, then I have O is somewhere here, just a, then I have N is here, and then this is, there is a vertical section, that is H, and then this angle is beta, and this point is C. Then I have P is somewhere a point here, and then I will call it, sorry, P is the point here, P is OP, and then this angle is called gamma, this angle is theta. And then if I draw a perpendicular from here to here, and that I call this perpendicular angle, and let me call this P prime, and this is another perpendicular draw from here, I call this P double prime. So, my vertical shift is H, this angle is beta. So, what will happen to H will be, this angle is beta, and then this is what is Mn, okay, H is the vertical shift, then H will be, and this distance is A, because this is the radius of the circle. So, H is equal to A, because H by A is sin beta, A sin beta, H is equal to A sin beta, and again my A is equal to so, which also I can write it as okay, H is equal to A sin beta. Again, now this distance further I will come back to this. Now gamma is small, if gamma is small, then we have if gamma is small, then we have cos gamma is 0, cos gamma is almost 1. Now, what I will do? So, A sin beta, since beta is small, I can call it as A beta, assuming beta is small, which can be equivalent to A beta, and A is nothing but we have ON is BE, and then we have this distance MO is B, this is B. So, I have Mn equal to B plus BE, Mn is B plus BE, and then it is because of that since beta is small, I can also call this as b plus b e into beta. Since beta is small, I can call A, because H is a small shift. So, I can always say A is equivalent to B plus B. So, this is same as B into 1 plus E into beta. Now, this is H. Now, what will happen to OP? OP is OP double prime plus P prime double prime P prime plus P prime P, and this is nothing but this is now. So, this will give me, or we can write it as, so this will give me A, because this is P prime P, P prime P is A cos gamma, because this is A and this angle is this is A cos gamma, plus P prime P double prime, P prime P double prime is okay. Now, this angle is theta. So, this is pi by 2 minus theta, again this is a perpendicular line. So, this is also theta, because this is pi by 2 minus theta. So, this angle is again theta. If this angle is theta, then if I draw a parallel here, I draw a line here, then it can be easily see that P prime P double prime will come as H sin theta plus, because this will be, if you draw a perpendicular. So, this angle, this will be parallel to this is again a perpendicular, this is a perpendicular, this is a perpendicular. So, this line is same as this line. So, this is nothing but from this to this distance is called H sin theta. So, similarly, P, as a result these are parallel lines. So, this will be P prime P double prime will be H sin theta, then plus OP prime OP double prime, and this will be give you, this is B E, this angle is theta, this is the perpendicular. So, this will give you B E cos theta. Yes. So, if I do that, because cos gamma is gamma, then this becomes A plus we have H is A sin beta, A into, that is B plus B E, B plus B E, B plus B E into beta, B plus B E into beta into okay plus B E cos theta, beta into sin theta plus B E cos theta, and this gives me A G plus A G, again my A is B plus B. So, this becomes B plus B E, again beta is small and E is small. So, this is B beta. Then since beta is small, this also I can write it as B plus B E plus B beta sin theta, B beta sin theta plus B cos theta. Assuming B E into beta is small, thus neglected, thus So, E beta will be 0. So, this term will go. So, B plus B E, B plus A is B plus B E. So, B beta sin theta plus B E cos theta. So, this is what O P, and what is O P? O P is nothing but O P is nothing but this is R angle gamma, this is the angle gamma, and O P is R. So, this that is becomes R is equal to. So, if this is the case, then what will get? Then we get R by B is equal to 1 plus E 1 plus E cos theta plus beta sin theta. So, in the same manner we can get what will happen to B by R 1 by 1 plus E 1 plus E plus E cos theta minus B sin theta. Plus beta sin theta. If I do this, then I expand it in a polynomial expansion. If I do, then it will give me 1 minus E cos beta, E cos theta minus beta sin theta. And once B by R is this, because I am neglecting the higher powers. Then if I go back to the Joukowsky transformation, my zeta is equal to z plus b square by z, and that is nothing but b into r by b. I am not going to the detail, we have already done this, plus b by r cos theta plus I into r by b minus b by r into sin theta, which gives me. So, now if I substitute for, so my this will give me, if I say b into r by b plus b by r, if I add these two, that will give me 2b cos theta plus I times 2b r by b minus b by r. So, 1 will get cancelled. So, that will give us E plus E cos theta, or this is E cos theta plus beta sin theta, E cos theta plus beta sin theta. Okay. So, then it will be 2b 1 plus E plus E cos theta plus beta sin theta. Sin theta into sin theta, and thus my xi is equal to 2b cos theta, zeta is xi plus I eta, and hence and my eta is equal to 2b 1 plus E cos theta, okay, 2b E into 1 plus cos theta plus 2b beta sin theta into cos theta into sin theta, sorry, eta is equal to 2b E 1 plus cos theta 1 plus cos theta into sin theta plus 2b beta, this is sin theta, this is again sin theta, sin square theta. So, that is my eta and this is my xi. So, this is my xi and eta. If I plot this, how it will look like? So, then what I will get in the zeta plane, this is my zeta plane. If this is the zeta plane, in fact, this will look like sorry, this will not be like this, rather I will put it in a proper manner. It will be something like this. In the previous case, we have seen that this was symmetric along the about the xi axis, but here there is a shift to the right, to the upward direction. So, this point I call this as my minus b, or rather I will call this is my, if I take anywhere on the axis, if this is my eta 1 and then I say this is my eta 2. So, anywhere the thickness of the aerofoil will be eta 1 plus eta 2, and then what will be my total length? Length will be 4b. So, this distance, the total distance, this is 4b and this is just because 2b 4b, and further I can have what will happen, length is 4b and the thickness will be eta 1 plus eta 2. Another thing we can see here, that when beta is 0, if beta is 0, then my xi will be 2b cos theta and my eta will be 2be into 1 plus cos theta into sin theta, and in that case my aerofoil will be a symmetric aerofoil. It should be like this, whereas this side there is a sharp edge, and this is what my symmetric aerofoil. Whereas this is my cambered aerofoil. And if we will see that always in this case the pressure distribution will be uniform, because it is symmetric in the both the sides about xi axis. On the other hand, here the pressure will be, because this side the pressure will be maximum compared to this side, because there is a vertical shift. So, the pressure it will be. So, perhaps this is the reason why, and the pressure, because there is a maximum pressure is higher in this side. So, it is the one of the reason why it will be acting as a lift force, because the pressure is more here on this side of the surface compared to the upper surface. So, always this will provide a additional pressure thrust, and that will act as a lift force in a aerofoil. On the other hand, if you look at this one, we call this this is the leading edge, this is also called the trailing edge. And soon we will see that this edge there is a singularity, that I will come to say compared to this. Here there is no singularity, but at this end that will come to see. Now let us look at what is the thickness, maximum thickness the aerofoil can have. If you look at the thickness T, as I mentioned, T will be eta 1 minus eta 2, and eta 1 minus eta 2 rather then my eta 1 will be, for the same angle theta, it will be 2be into 1 plus cos theta 1 plus cos theta 1 into sin theta 1 plus 2b beta sin square theta 1, and my eta 2 will be 2be 1 plus cos theta 2 into sin theta 2 plus 2b beta sin square theta 2. But since my eta 1 is equal to 2b cos theta 1 is same as my xi 1, because if I look at this, if any point I am considering this is my eta 1 and the same perpendicular point is eta 2. So, my xi is fixed. So, xi is 2b cos theta 1 is same as 2b cos theta 2, which implies my theta 1 is minus theta 2. Theta 1 is theta 2. That means, in the this will be minus theta 2. So, the angle in this way, if I say this, so the theta 1 and theta 2 are negative. So, in that case my t will be eta 1 minus eta 2, because this distance minus this eta 1 minus eta 2. So, the total distance, and that will be, we can see that will be give us, if you add eta 1 minus eta 2, that will give you, rather it is eta 1 plus eta 2, this is eta 1, this is eta 2. So, then that will give me 2be into 1 plus cos theta. So, this is eta 2, this is eta 1, sorry, this is eta 1 minus eta 2. So, 2b 1 plus cos theta, and this I call it as okay theta, say 2b 1 plus cos theta into sin theta, because 2b beta sin square theta, this will be minus, this both will be same. So, this will contribute plus 2b into 1 plus cos theta into sin theta, and that is nothing but 4be cos theta into sin theta. So, now if it t is this is the maximum, this is the thickness, that is t, then what will happen to the total chord is 2b, chord length is 2b. So, thickness, total chord length is 4b. So, if I just say that thickness to chord length ratio thickness to chord length, that will be 4be into 1 plus cos theta into sin theta divided by 4b, that is nothing but E into 1 plus cos theta into sin theta. So, again it can be like, if you look into the same way, what will happen to when dt by d theta, if you look at dt by d theta is 0, we can always see that theta is equal to pi by 3, and theta is equal to pi by 3 will give us the maximum thickness. Give a maximum for t, and if theta is pi by 3, pi by 3 will give a maximum, and again we will see that theta is equal to, when it becomes pi, theta is equal to pi, again we will see that will give a minimum. this will give us minimum, and that shows that in fact we have seen in that case, then what will the maximum, thus what will happen, then in that case T maximum will be thickness to core length ratio maximum will be, again we will see. So, this thickness to core length and that will be E into 1 plus cos pi by 3, that is 1 by 2 into sin pi by 10 root 3 by 2, and that will be into 3 by 2, 3 into root 3 by 4, and this will be the value. This is the maximum, this the maximum of this value will be this, and this is what the same result we had got in case of a symmetric aerofoil. Now again we can see, suppose, so this is what we are looking for. So, we have got the result for a cambered aerofoil, and we also see that in the case of the cambered aerofoil also we get the maximum value when theta is pi by 3, and it is again minimum when theta is pi. Another thing, what will happen if there is the next transformation I look into, of a circle into a circular arc. Let me say what I am looking for this. In the previous two cases, we have seen that we have shift the center of the circle. We have origin is here, we have always shifted the center to the first initially to the right, and then initially there is a vertical shift. But what will happen? There is no vertical, no horizontal shift. There is no horizontal shift. So, this is the, rather I will say, sorry. So, suppose there is no horizontal shift, the center is shift here, only a vertical shift, this is origin. Then what will happen? In that case, if we will go back to the previous formula, then from there we can easily see that there is no vertical shift. So, E will be 0, and once E is 0, then what will happen to my eta? E is 0. So, my xi will be 2b cos theta, whereas on the other hand my eta will be 2b beta sin square theta, 2b beta. So, that will be 2b beta, because theta will be the same as any point, there is no horizontal shift. So, in that case what will happen, my I will get a foil like this, whereas this distance is 2b beta, maximum it will be here, eta can be maximum 2b beta. So, in this case here only shift is in the vertical shift, and that vertical shift is nothing but 2b beta. Now, there is nothing on the horizontal side. So, this is a, so from again I am just taking this result from the cambered aerofoil as a particular case, I will say particular case of a cambered aerofoil. So, what we have understood by now, we have seen that by using the Joukowsky transformation from a from a circle, we can always come back to a cambered aerofoil, a symmetric aerofoil, or a circular arc. And now let us see how this, because we have seen that in case of a aerofoil we have a trailing edge, we have a leading edge. What happened at the trailing edge, particularly when a z is equal to minus b? So, the nature, let us look at the nature of the trailing edge of the trailing edge. In this case, we have seen always zeta is equal to z plus b square by z. Then what will happen to d zeta by dz? It should be 1 minus b square by z square. So, which implies d zeta by dz will be 0 for z is equal to plus minus b. So, z is equal to plus minus b. Now, what will happen to the point zeta is equal to, rather now what will happen when z is equal to b? If z is equal to b, my zeta will be, z is b means beta is 2b, z is equal to b, beta is 2b, and z is equal to b is a point because of the circle, it will be a point. If I look at my circle, the point z is equal to b, because I have taken this point as center is somewhere, c is somewhere here, and this distance, total distance is 2b, b plus b. So, always the point b will be somewhere inside, particularly since if you look at the aerofoil, because this distance, total distance is 4b and somewhere 0 is here. So, it is minus 2b to 2b. So, my b will be a point inside, but what will happen if z is equal to minus b? If z is minus b, which implies zeta is equal to minus 2b. So, minus 2b is a point here. So, this is point is minus 2b. So, that means the trailing edge when z is equal to b, zeta is minus 2b, and in that situation, so this will be the point z is equal to minus b will transform on the circle, will transform to zeta is equal to minus 2b on the aerofoil. Rather, I will say on the circle z is equal to b will transform to zeta is equal to minus 2b on the aerofoil, that is the trailing edge. And now, I will look at how this will behave near the trailing edge. Now, let us see, we have already seen, we have zeta is equal to z plus b square by z. It can be easily seen that z plus 2b by zeta plus 2b by zeta minus 2b, it will be, can be easily written as, if you substitute for zeta is z plus b square by z, you will see that it will be z plus b by z minus b whole square. So, the point, so this itself shows that. Now, what I will say, let me take any neighboring point of zeta in the neighborhood of zeta is minus 2b. If I say zeta is minus 2b plus s e to the power I chi, and my z is minus b plus r e to the power I theta on the circle, that means I am considering a circle. This is a point b, and then I consider aerofoil, and I consider this is the trailing edge corresponding point here. Then if I substitute for this zeta and z in this expression, then I will get s e to the power I chi by minus 4b plus S e to the power I chi equal to this is z is equal to minus b minus b, this will be r square e to the power twice I theta divided by, that is z is minus b into b minus b, rather minus 2b, z is minus b minus b, then minus sorry, z minus b, z is minus b plus r e to the power I theta. Now, since r and s are small, so which I can write it as s e to the power I chi by minus 4, because this is a small quantity compared to this, so this can be neglected, by 4b, it will be r square into the power 2 I theta by b, because this will be, or this is square, so this will be by 4b square. So, 4 get cancelled, b get cancelled, which implies s e to the power I chi is equal to minus s e to the power I chi is equal to r square into the 2 I theta, which also I can write it as s e to the power I times chi plus pi is equal to r square e to the power 2 I theta. So, that means a point at this edge, if there is a shift here, there is an increase in theta, then a small increase here, that means here it will be pi. So, what it will show me, that will show me that as if my chi plus pi, if I look at the compared angles, chi plus pi is a 2 theta, and that shows if I move around the point B, if theta increases by pi, theta will increase by pi, then what will happen? Chi will increase. If theta is increases from 0 to pi, that will be 2 pi, and that means, and then chi will increase by pi, And again another thing is that, but I have two edges up there. I have two edges of the aerofoil. There are 2 points, and then when again what will happen near the trailing edge, as chi will increase by pi, as the angle chi will increase to pi, rather will tend to pi, approaches pi, then it will touch the trailing edge. So, that means this angle will reach here, and here, so it will form a cusp. Will be formed. We have two surface here, but they are meeting at this point, and this is what. Now, with this understanding, I will say, now I will go to the another aspect, and what we call the, because we understood that here we have understood that in a circle at the point B, when the angle is reaching, there is a theta increase, theta is increasing by pi, then or the same angle here is increasing by, or chi will increase by 2 pi. Sorry, because this will be 2 pi, otherwise it will not. Now with this understanding, let us go back to the Joukowsky hypothesis. This is very simple. To understand the Joukowsky hypothesis, I will do one thing. Let me say that q is the speed. Suppose look at this, let B is a point here. Let q is the speed at B, which transform to the trailing edge, into the trailing edge. Of the aerofoil. And q prime, let q prime be the corresponding speed, be the speed at the trailing edge. Then what will happen to q prime? Q prime is dw by dz, and that is nothing but dw by d zeta into d zeta by dz, and this will be modulus, and this will give us dw by dz is q mod into d zeta by dz, and d zeta by dz we have seen this, we have seen that so which can also be written, so which implies my q will be q prime by d zeta by dz, and this d zeta by dz we have seen d zeta by dz is 0 at z is equal to minus b. So, that means q will tend to infinity at z tends to minus b, because our d zeta by dz is 0 for z is minus b. So, this will be q will tend to 0 infinity as a. So, this is important. So, that means the q is the speed at z is equal to minus b. So, that what will happen in that process, the corresponding point, because the point z is equal to minus b will correspond to the trailing edge. So, we have a the speed will be infinite there. So, but so thus hence near the trailing edge, the speed will be large, speed will be extremely high, will be singular, will be high, that is the flow is singular, flow becomes singular. So, but in reality, if this is at the trailing edge, we should have a flow should be regular. So, to avoid this, to make the flow regular, what Joukowsky proposed, that that then comes the Joukowsky hypothesis. The Joukowsky hypothesis says this hypothesis says the circulation in the case of a properly designed aerofoil adjust itself in such a manner so that B is a stagnation point. And thus the velocity at the trailing edge becomes finite. In fact, this is obvious because we have already seen that our q is q prime modulus by d zeta by dz, and this will be 0. So, this has to be form of 0 by 0, then only it can lead to a finite value. It has to be a finite value if this has to be 0 by 0 indeterminate form, and so for that q prime, unless q prime is 0, we cannot achieve this. So, for this is what Joukowsky. So, this is what Joukowsky hypothesis says, that somehow we have to introduce a circulation in case of a properly designed aerofoil and adjust itself. That means, we have to introduce a circulation in the flow, so that in such a manner, so that B is a stagnation point. So, the point B what I have described, that will behave like a stagnation point, and once it is a stagnation point, the flow speed will be 0 here. Once the flow speed is 0, then this will be d zeta by dz will be 0. So, that will be give a 0 by 0 form, which in if I approach the limiting case, then in the limiting case this will give us a finite value. This is what Joukowsky hypothesis says. Now, with this understanding, now we have understood that in case of a aerofoil near the trailing edge, we will have a singularity, flow singularity, and to avoid the flow singularity, the near the trailing edge a circulation has to be introduced in such a manner, so that the near the trailing edge the flow, there will be a stagnation point will be developed near the point, and that will lead to the velocity near the trailing edge, which will lead to the velocity near the trailing edge to be finite, and that is what Joukowsky proposed in his hypothesis. So, this is what I want to talk in this lecture, because we have already seen that how the behavior of the trailing edge. Now, another major result in this case of aerofoil is the theorem of Kootenay and Joukowsky, and once we know that Kootenay-Joukowsky theorem, then that will give us, because we have already been exposed to that in case of a cambered aerofoil, we have a lift will be developed, because unlike the case of a symmetric aerofoil, in the case of a cambered aerofoil, the two sides of the aerofoil there is a pressure difference, and that will lead to that there will be a pressure difference, and that pressure difference gives us, because on the upper side there will be less pressure, on the lower side there will be more pressure, and in the process there will be a lift. That will be the main reason for the development of lift in the aerofoil in case of a cambered aerofoil. And this lift and moment, as I have yesterday's earlier lecture I have told that the lift can be and moment can be calculated by using this Blasius theorem. And on the other hand, if we will go back to the drag, because we have seen that in case of a circular cylinder, we have seen that D'Alembert's paradox says that there is no drag force in case of a cylinder. So, since we are transforming a circle to a aerofoil, so we will not able to get a correct picture of the drag force in the case of a cylinder. In this case, in the case of aerofoil, however, the lift force will get almost accurate realization of the lift force here. And in the next lecture, I will tell you about the Kootenay-Joukowsky theorem, which calculates the lift and the moment that is acting on the aerofoil. With this, we will stop here today.